So in this video, we are going to talk about Wronskian and the Abel's formula. So you guys already know what a Wronskian is. I think from your 102 or in your essentially the previous courses which you have taken. But for now, again, let me explain to you what Wronskian is for the system. Okay, so let us look at this thing. Let us write it like this. Let's say that you have two solution. So function. So given n vector valued function, right? And it is given by u1 of x, u2 of x, un of x. Clear? We write it like this. Okay, the determinant, we are going to define a determinant. The determinant, okay, determinant w of u1 u2 un. I want to define something like this. See, so essentially you have, if you are given this thing, given n such functions, we want to define the determinant. So essentially, if you want to write it, it is just u1 and the components of u1 in column. Okay, so 1 1. Of course, these are all functions of x. Let me write it, it will be easier to understand. Now un of x. So basically, all of these functions, these are vector valued functions. So each so you see each ui is a function from I to r, right? Okay, sorry, rn, I to rn. Okay, and hence ui of x is n tuple, right? Okay, so ui of a, so ui you want to write it in the ith column. Okay, so this is u1, the second this thing component, and u1 the nth component of x, and it goes on like this. This is the first component, un second component, and this is the n component. Okay, so that is going to be your Wronskian. So this is called a Wronskian. Okay, so given so for example, let's say example, let's take this function u1 of x to be sine of x and cosine of x. Okay, and u2 of x is minus cosine of x and sine of x. Okay, and now let's write down what the Wronskian is. Let's see what the Wronskian is. So the Wronskian of so this is for n equals to 2. This is the case of n equals to 2. Okay, so the Wronskian of u1 u2, in this case u1 and u2, is given by just put all of this together. Okay, sine x cosine x minus cosine x sine x. That's the Wronskian. Okay, and of course you can calculate this thing, and that is going to give you 1. Okay, fine. So what is so special about Wronskian? Now, one small detail which you can check is this. So you check that if you guys already did a 102, so basically a previous ODE course, okay, you guys already know what a Wronskian for a second order linear equation is, right? So for a second order linear equation, let's say it will look like this: y double prime plus ay prime plus by equals to it does not matter, let's say 0, homogeneous problem. Now and so you want to talk about Wronskian of y1 and y2. Okay, where y1, so and let's say y1 y2 are two solutions, okay, so I want to talk about what is the Wronskian of y1 and y2 in this case. Yeah, I am quite sure you guys already know what is that. It is y1 y1 prime and y2 y2 prime. Okay, now how is this different from what we did for this case of system? What I want you to check is this. You see, so what you do is this: convert the second order linear equation, okay, equation to a system, and what I want you to do is, see here the function contains the function itself and a derivative. Okay, so and what I want you to do is compare the two Wronskians. Compare the two Wronskians. I hope you understand that they are going to be the same type of thing. Yeah, two Wronskians. So you understand, for any system, the Wronskian is given like that, the earlier thing, and for any second order equation, Wronskian of two solutions looks like that, right? Now, what I want you to do, I want to compare those two Wronskians and see that if you convert a second order linear equation into a system, then essentially it is the same thing. Clear? Okay. Now, so that's your Wronskian. Now, what is so special about Wronskian? That is what we want to see. Okay, so for that, what we are going to do is write down a small theorem. Okay, so with the help of the last example, you have seen that in the last video, we have seen that if u1 and u2, if you define it like that, okay, then we showed that these are linearly independent, right? And now we are seeing that the Wronskian is basically not 0 here, so it is 1. Yeah, so we want to see if there is a relation between this sort of thing, that if the Wronskian is non-zero, is the functions linearly independent or not, that sort of thing. Yeah, so let's write down a theorem. If the Wronskian wx of, now for now let me do it for n equals to 2. I mean, you can do the exact same thing for any n. Yeah, so nothing special about general n of two vector valued function u1 of x and u2 of x is different from 0, okay, in at least one point, okay, x naught in, and let's say I, okay, then they are linearly independent in I. Clear? Linearly independent is not like they are linearly independent at one point. Huh? If we are saying, if we are talking about two functions and if we are saying they are linearly independent, it means they are linearly independent in a whole interval. Okay, right. Now, what is the meaning of this thing? So you have two vector valued functions u1 and u2, and they are different at one point. See, the importance of this theorem is this. Now, this theorem says that if you can show, if you want to show that two vectors are given and if you want to show that they are linearly independent, then showing linear independence at one point. So if you are showing that the Wronskian is non-zero at one point, that is enough to show that they are linearly independent in every point in I. Okay, so very, very strong statement. Okay, so let's look at the quick proof of this statement. Proof. So the proof contains something like this. So it goes on like this. So you have to show that this is linearly independent. Okay. So let us assume that u1 and u2, u1 of x and u2 of x are, so let u1 of x and u2 of x are linearly uh, dependent, right? In I. So essentially I have to show linearly independent. I am starting with a contrapositive statement. I am saying that for a contradiction, let us let us assume first of all that they are linearly dependent and see what happens. So if they are linearly dependent, so you can have there exists something, C1 and C2 such that C1 U1 plus C2 U2. Of course U1 and U2 are functions of x, I'm not writing here. So this is equals to 0 in I, okay, with mod C1 plus C2 non-zero. Clear? Okay. So with that condition there, it is linearly independent means at least one of the C1 and C2 is non-zero. So essentially this condition holds. Okay. And this is essentially same as, so if you break it up, see U1 has two components. So that is, if you break it up, it is C1 times U1 1 U1 2 plus C2 times U2 1 U2 2. This is 0 0, right? That is 0 0. So what does that give me? That gives me that this is actually equivalent to saying that the system, this system of homogeneous equation, and the system looks like this. So you understand the system, right? It is okay, let me write it. U11 C1 plus U21 C2 and U12 C1 plus U22 C2. This is 0, this is 0. Okay, that's the system. So you are basically saying that this system, okay, what does it have? It has a, so what sort of solution can you expect from this system? Of course, C1 equals to C2 equals to 0 is always a solution, okay? But that is not the case here, because we want, we have C1 and C2 non-zero, right? It is given. It is given, okay? So essentially what we can say is, if you look at this system of equation, okay, this system of equation has a non-trivial solution. That is what it means. Is this fine? Okay. So how do I put it? I should write it here as 1. Okay. So that implies 1 has a non-trivial solution. Trivial solution. Clear? Okay. Now you see, if this has a non-trivial solution, okay, then what can you say? If this homogeneous system has a non-trivial solution, when can it have a non-trivial solution? Yeah, it can have a non-trivial solution if the Wronskian of x, okay, this is going to be 0. Is this clear? See, the argument is this: if they are linearly dependent, this relation C1 U1 plus C2 U2 is equals to 0, that in I holds for at least some C1 or C2 non-zero, right? Now this relation, so I'm not talking about C1 C2 non-zero right now, okay? So what happens now is this relation will imply that C1, so if you just break it up, it will give you two linear system, right? Homogeneous equations, yeah? Linear equations. Now this linear equation, this will always have a non-trivial solution if the Wronskian of x is 0, okay, for all x, yeah, for all x in I, yeah. I hope that is fine. You guys can, what is the Wronskian of this thing? It is basically, you can write 1 as, this is basically the you understand, the matrix, the Wronskian, okay, I hope I'm not doing this part, but it's quite clear, right? That if this is a system, right? So basically, if you look at the coefficients of this thing times C1 C2, you just write down the coefficients: U11 U12 U21 u2 2, right, times c1 c2. This is equals to 0 0. That's your matrix right now. This matrix, when the c1 equals to c2 equals to 0 is always a solution. Yeah, if you want a non-trivial solution, then of course the determinant this particular thing, or the determinant of this particular thing has to be 0, right? Now that's from your how do I put it, the theory of linear equations, right? So for this one to have a non-trivial solution, if and only if the Wronskian of x has to be 0, huh? But it is given, but the Wronskian of x not is non-zero given to us. Okay, so that will imply that the function u1 and u2 are not linearly dependent. Clear? And hence they are linearly independent. Okay. See here, c1 and c2 non-zero given to you. So what does that say? It says that if c1 plus c2 is non-zero, so basically it is saying that there exists a non-trivial solution for this system. If there is a there exists a non-trivial solution for this system, that means the Wronskian has to be 0 everywhere, right? But you know that there is a point x0 where the Wronskian is non-zero, so that will imply that the two functions are linearly they are not linearly dependent, and hence they are linearly independent. I hope this proof is fine. It's very easy proof, yeah? But yeah, okay, so you need to do that. Okay, fine, so that's there. Now with this thing, let us look at one simple instance, okay, that if let's say that the two functions, vector valued functions, so remark, let me put it this way, remark, given two vector valued functions, okay, which are linearly which are linearly independent in the interval I, okay, which are linearly independent in the interval I, then what do you think the Wronskian is? So basically what I am trying to say is, given two functions u1 e2, I want to check what is the Wronskian of this is. So essentially what I am asking is, do you really think this is always going to be 0, or it is not going to be so either Wronskian is 0 or not? That's the question. Okay, so let's take this example. U1 of x is x and 1. Okay, I'm taking this particular thing like that, x and 1, for a reason, huh? So u2 of x is x square and x. Okay, this is nothing but just to keep that part of thing. See, there is nothing special about x1. I can write it as 1x and x square. Why I am writing it like this? Because just to keep for the second order equation, you write the function and the derivative like that, right? The function and the derivative like something like this. Yeah. Okay. So that is given to us. Now, I am quite sure you guys can check that u1 and u1 and u2 are linearly dependent. Of course, they are linearly independent. They are linearly independent, of course, because u1 is equals to constant times c x times u2. So they cannot be linearly dependent, right? Okay, so they are linearly. That implies they are linearly independent. But if you look at the Wronskian of u1 and u2 at every point x, so this is hold for every in the whole R, that is going to be 0. Okay, whatever the interval is I. Okay, so the Wronskian, the linearly independent thing, if there are two functions which are linearly independent, that does not warranty or guarantee that the Wronskian is going to be non-zero. Clear? So for that, there is a small theorem here. So what does the theorem say? The theorem says that if u1, u2, un of x. Okay, so all of these functions are functions of x. I am not writing all that. So that is okay. Let me write, otherwise some of you may get confused. Are linearly independent. Okay, solutions. So you understand? See, essentially, our idea is something like this. If they are linearly independent, then the Wronskian must be non-zero. But here we saw an example where the two functions are linearly independent, but the Wronskian is going to be zero. So for now, what we are going to do is we are going to start with n linearly independent solutions, u1 into un, and their solutions to what? Solutions to let's say y prime equals to ay. So you are given a system, so homogeneous linear system, clear. And for that homogeneous linear system, let's say you have n solutions, okay, linearly independent solutions, that's important. Yeah? Then the Wronskian of x is non-zero, okay, non-zero for all x in I. Okay, I am quite sure you guys understand what I'm trying to say here, that given any two arbitrary functions, if they are linearly independent, there is no guarantee that the Wronskian is going to be non-zero. Okay, but if there are linearly independent solutions, yeah, they are solutions of system like that, y prime equals to ay, then they are non-zero. Yeah, so you can prove that. So let's look at the proof of this particular thing. So the proof. So we start with the x naught, where the so let w of x naught. So I have to show that the Wronskian is non-zero for all x. So let's start with a point x naught where the Wronskian is zero. Let's say. You understand what I'm saying? So let us assume that there is a point x naught where the Wronskian is going to be zero. Okay. Now, if that is the case, then there exists C1 and C2 with mod C1 plus C2 not 0. So basically I want them to be a solution. So basically which are solutions to this particular thing, that one second, let me. So basically what I want is, okay, I have n equations, right? So I mean, for now let's just start with the two equations. I don't want to deal with n equations, that's what. Otherwise I mean, you can do it for n equation, no issues here, but for two equations and u2x, okay. Let's say there are two equations. If there are n equations, you got to the c1 c2 cn, that's all. I mean, nothing changes. Which are solutions to this system. Now what is the system? The system is c1 u1 at the point x naught plus c2 u2 at the point x naught. This is 0. So if you are looking at this system, of course at the point x naught, if you are looking at the system, this is a system of equation, right? Because u1 has u1 1, u2 1. So you can write it as a linear system, right? 2 cross 2 system. So essentially, if the Wronskian is 0, you guys can understand that that system has a solution, non-trivial solution. I am just writing that solution as C1 and C2. Clear? Okay. Now what you are going to do is, I am going to look at that C1 and C2. I am going to use that C1, particular C1 and C2. Clear? Okay. Now, you see, if u of x, you define a function u of x which is c1 u1 plus c2 u2 at the point x, okay. Now this function, if I am defining it like this, what do you think happens to this? See, if u1 and u2 are solutions of this problem, okay, so u1 prime equals to a u1 and u2 prime equals to a u2, then I mean by superposition, by principle of superposition, what can you say? I can say that what can I say? That u prime equals to a u. You understand that u is a vector valued function, okay? So u has two components here. So u prime equals to a u. By superposition, you can say u prime equals to a u. Clear? Okay. Now, for those constant, you see this c1 and c2 is not arbitrary c1 c2. These c1 and c2 are those non-zero. Oh, okay, I have found a non-zero pair, right? of C1 C2, and I am using that pair to construct a new function ux which looks like that. Okay, u1 and u2 is given to you. I will start with a c1 u1 plus c2 u2 and call it a u of x, and that u of x, of course, by superposition u satisfies this thing, and hence it solves the equation, right? Solves the equation. Okay, so once it solves the equation, what does that say? So if it solves the equation, and what is ux naught? Let's see what is ux naught. So it solves the equation, of course. And what is u of at the point x naught? It is c1 u1 at the point x naught plus c2 u2 at the point x naught. Okay, now what do you think the solution is? See, c1 u1 at the point x naught plus c2 u2 at the point x naught is given to be the zero vector. So essentially this is the zero vector. Clear? So what does u do? Hence, therefore, what does u do? U prime equals to a of u, and u at the point x naught is 0. Okay, now one thing which I did not do for you guys, right, I mean up till now, is there is something called the existence and uniqueness theorem. It's actually the Picard's theorem, okay, in a different form. So basically, for now, let me just write it down, and later on we'll prove, while we prove Picard's theorem, all of this will, I mean, follow. So basically, by existence and uniqueness theorem, okay, this is not your usual existence uniqueness, but for a existence uniqueness theorem for system of equations. This problem, so it's a homogeneous problem, right? Homogeneous problem, can you think of one solution? Of course, 0 0 is always a solution, and u at an initial point is 0. So basically, u equals to 0 everywhere. That is one solution. But existence uniqueness theorem says that this homogeneous solution, if it takes 0 at one point, it has to be 0 everywhere. So basically, the solution is unique. That implies that u of x, this is equivalent to 0. Okay, this is equivalent to 0 for all x in whatever interval it is I. Okay, and of course this 0 is not your usual 0. Please remember that, right? 0 is component 0, so vector 0 0 0. Okay, so by existence uniqueness theorem, ux is 0. So that's your existence uniqueness. If you want to write it properly, let's say if you so existence, let me write it down. The existence uniqueness theorem says that u prime equals to a of u, and u at the point x naught, let's say that's your u naught. If this is the equation given to us, then that equation has there exists a unique solution. Okay, solution and globally. Okay, there exists a unique solution globally. So basically in I, whatever the interval is I. Okay, that's the existence uniqueness. Now from existence uniqueness, what does it guarantee? It guarantees that ux is going to be 0 everywhere. Okay, now if ux is going to be 0 everywhere, that will imply that c1 u1 at the point x plus c2 u2 at the point x is 0. This kind of relation holds with mod c1 plus mod c2 not equals to 0. Why this is the case? Because this c1 and c2 is such that mod c1 plus mod c2 is non-zero, right? That's our construction. So basically, what do we get from one point? This is the one point given to us. See, this is the one point given to us. Okay, the equation itself actually guarantees that you can actually have that for every point. So if it holds for one point, it holds for every point. Okay, fine. So what does that say? It says that C1 and C2 are linearly dependent, right? It says that C1 and C2 are linearly dependent. Okay, so that will imply that sorry, not C1 and C2, U1 and U2 are linearly dependent. Okay. One second, let me I'm doing some mistakes somewhere. Yeah, so that will imply that u1 and u2 are linearly dependent, but you have u1 and u2 are linearly independent, right? It is given to us. So what is going on? That's a contradiction. So basically what is going on is there cannot be a point x naught where Wronskian is 0. You understand? Okay, So that's the contradiction. Okay. So that is proved.